Hello there, my good peeps. This is an Algebra 2 video. It's Chapter 3, Section 8. It is the last section in this chapter, and it is solving systems of equations using inverse matrices. And so before we begin, whenever you talk about inverses, you kind of have to talk about identities. And you have used several inverses and identities in your mathematical career. For example, you all know how to solve a basic equation like this, because you know that the inverse of adding 4 is subtracting 4. And so we get this because positive 4 and negative 4 produces the identity, which is 0. 0 is what we call the additive identity because it's the one number you can add or subtract to any other number and it'll leave it the same. It'll be unchanged. And then we know that the inverse of multiplying is dividing. And again, we get x equals 1. So you've done this a lot. So you know that these are inverses. And again, that's because 3 divided by 3 is 1. And 1 is what we call the multiplicative identity for a similar reason, because when you multiply or divide 1 from any number to any number, then you get an unchanged answer. 5 divided by 1 is 5. 5 times 1 is 5. Just like positive 4 plus 0 is 4. 4 minus 0 is still 4. So you have this relationship between inverses and identities. And I just want to remind you of that as we begin this lesson, because it plays a huge role in how we're going to solve systems with inverse matrices. But before we can get started, we need to first have our identities identified. So for matrices, depending on, by the way, only square matrices have inverses. So a 2 by 3 wouldn't have an inverse. But square matrices that have the same dimensions, 2 by 2, 3 by 3, 4 by 4, then you have an identity. So for a 2 by 2 and for a 3 by 3, we have different identities. But they do have something in common, a couple of things. You can notice that they both involve only the numbers 1 and 0. Shouldn't be too astonishing, since we know for multiplication, matrix multiplication, that you do a lot of adding and subtracting. And so adding and multiplying. And of course, the multiplicative identity is 1 and the additive identity is 0, so it would make sense that those are the numbers that we find inside of the identity matrices. So the other thing that you'll notice is that they each have what we call a diagonal of 1s. And that is always the case with an identity matrix. So in the 2 by 2 case, you have a diagonal of 1s and everything else is 0. In the 3 by 3, diagonal of 1s and everything else is 0. So if you had a 5 by 5, you would know that it would be a diagonal of 1s and everything else would be 0. So we said earlier that when you have an identity matrix, it's supposed to leave the number unchanged. For example, we know that 5 times 1, because it's the identity, should get 5. You should get back to the original. If you have 0, same thing. When you're adding, if you add 0, it should leave it unchanged, back to the original. So what I have here is I randomly chose this matrix, negative 3, 2, 1, 5, and I am multiplying it by what we see here is the identity matrix. Now, according to what I've just been saying, when I multiply these two, I should get back the original. Just like 5 times 1 gave me the original, 5 plus 0 gave me the original 5. When I'm done here, I should get negative 3, 2, 1, 5. And so we're going to see if it works. At the same time, review your skills on multiplying. So a 2 by 2 times a 2 by 2 will yield a 2 by 2. And so we're going to go row 1, column 1. So it's going to be negative 3 times 1 plus 2 times 0 for that element. And then this element is going to be row 2, column 1. So it'll be 1 times 1 plus 5 times 0. And then over here, we're going to get negative 3 times 0 plus 2 times 1. And the very last one is row 2, column 2. So it's going to be 1 times 0 plus 5 times 1. Okay? And it's easy to do these because whenever you have zeros, it kind of makes things nice and easy. 2 times 0 is 0. 5 times 0 is 0. 3 times 0 is 0. 1 times 0 is 0. That's nice. So what you're going to end up with is -3, +2, 1, and 5. And so you can see that, lo and behold, I end up with the original matrix. So that is how identities work. And so the first thing that you have to be able to do is determine whether matrices are inverses or not. And that kind of goes to what I was saying earlier. The only way for you to be an inverse is if you produce the identity. Like -4 and +4 are inverses because they produce the identity, which is 0. 5 divided by 5 is 1. So 5 and division by 5 and multiplication by 5 are also inverses of each other because they produce the identity. So the only way to be sure that these are actually inverses is to multiply them and see if in fact they produce the identity. So we're going to go ahead and do that now. So again, 2 by 2 and a 2 by 2 is going to give you another 2 by 2. So this is going to be -4 times 1/4, and then 2 times 1/2. Then I'm going to get -2 times 1/4, and 1 times 1/2. So I'm going row 2, column 1. And then over here I'm going to go row 1, but column 2, which is -1/2. And then I'm going to get row 2 and column 2, like that. And so when I simplify this stuff, -4 times 1/4 is going to just be -1. 2 times 1/2 is going to be +1. And then here I'm going to get -2 divided by 4, which is going to be, excuse me, this is 1/2. And then this is going to be -1/2. Over here, negative times negative is positive. 4 divided by 2 is 2. And then this is -2, +1, and -1. So when I add them together, 1 minus 1 is 0. 1/2 minus 1/2 is 0. 2 minus 2 is 0. And 1 minus 1 is 0. So basically I get 0, 0, 0, 0. But that is not the identity. I'm supposed to get a diagonal of 1s, and I didn't. So in this case, in part A, the answer is no. They are not inverses. And then we go to part B and do the same thing. Excuse me. I am under the weather, obviously, so I hope that doesn't bother you too much. But let's try this guy. 3 times 3/4. And then we're going to add that to -5 times 1/4. And then I'm going to have to move this little strip here because it's kind of in my way. And then we're going to go 3 times 5/8. If you can't read that very well, that's a 5/8. And add that to -5 and 3/8. Like that. Okay. All right. Now we're going to have -2 times 3/4 and 6 times 1/4. Then we're going to have -2 times 5/8 and 6 times 3/8. Like that. Okay, so now we're going to simplify this little guy. So 3 times 3/4 is 9/4. So I want to come over here and put 9/4. -5 times 1 is -5. 5/4. 3 times 5/8 is going to be 15/8. And negative 5 times 3/8 is negative 15/8. And over here we're going to get negative 10/8. And 6 times 3 is 18/8. Over here we're going to get negative 6/4 and positive 6/4. So what's going to happen is 9/4 minus 5/4 is 4/4, which is 1. Negative 6/4 and positive 6/4 is 0. 15/8 minus 15/8 is 0. And 10/8, negative 10/8 plus 18/8 is going to be 2/8, which is 1/4. Now, we were very close to that being a yes, so I need to figure out what happened there. I think this is supposed to be a yes, so I think I must have messed up somewhere. Let's just make sure that I have this right. Negative 2 times 3/4 plus 6 times 1/4, and then negative 2 times 5/8 plus 6 times 3/8. Oh, I'm sorry. I know what I did. I put 18 minus 10 is 2. 18 minus 10, I'm sorry, I don't know what's going on here. My brain is, I'll blame it on the illness. But at least I figured it out. Okay, so 18 minus 10 is actually 8/8, and 8/8 is 1. So in this case, you do get the identity, and therefore your answer is an overwhelming yes. All right, so now I want you to try this little guy and then determine whether it's a yes or a no, and then we'll move on to the next example. And the next example is about inverses. So we already talked about the importance of inverse and identity and how they're tied together, but I need you to know how to find an inverse. So given you have a matrix, it's a 2 by 2, that has elements A, B, C, D, then the inverse, and the notation for inverse is just this little -1 here. Doesn't mean to the negative 1 power, it just means A inverse. So A inverse would be equal to 1 divided by the determinant of A. And if you don't remember the determinant of A from before, we use sometimes these bars to indicate determinant. And if you remember, the determinant was found by doing the diagonal, so A times D minus B times C. So the one that I squared off is the end all of the formula. But I wanted to talk to you about the matrix itself. This is not the exact same thing as A, B, C, D. What you do is you invert A and D, so the D goes up here, the A goes down there. And then you don't invert B and C, but you make them the opposite sign. So if this is B and C, this would be negative B and negative C. Now again, the reason why we call this the determinant, you probably didn't realize that why before. I mentioned it in the previous video, but I don't know if you caught it. It's called the determinant because it determines whether or not the inverse exists. The inverse does not exist if the determinant is 0. And the reason for that is because the formula says 1 divided by the determinant. And if the determinant is 0, you can't divide by 0. And therefore, you wouldn't be able to calculate an inverse. So it's important to note that there's the formula for the inverse. But if the determinant is equal to 0, then you have no inverse. All right, so now I want you to find the inverse for these two. So it wants me to find the inverse. So the first thing I'm going to do is find the determinant. So the determinant of P is equal to 7 times negative 1 minus negative 5 times 2, which is going to be negative 7 minus negative 10, which is the same thing as negative 7 plus 10, or simply 3. That is not 0, and therefore in this case the inverse does exist. So the inverse will be 1 divided by the determinant, so 1 divided by 3. And then I will flip around some numbers here. I will flip around -1 and 7. And then the other two numbers will become the opposite sign. So the -5 will become +5, the +2 will become -2. And my last step is to distribute the 1/3 to get my final answer. So P inverse will equal -1/3, -2/3, 5/3, and 7/3. And this would be my inverse. And then I do it again for Q. Again, the first thing I want to do is find the determinant. So the determinant of Q is -8 times 9 minus -6 times 12. And -8 times 9 is 72. And -6 times 12 is also -72, so minus -72, which is -72 plus 72, which equals 0. Now, because the determinant equals 0, that means that the inverse for a Q does not exist. So at that point, we stop. Okay, so now I want you to try do-it-yourself number 2, A and B. And then we will go to our final element of this lesson, which is putting all of this together, excuse me, into a matrix equation. And now, in a matrix equation, you kind of did some of this before, so I kind of want to just make sure. Sorry, I had to get some water to clear my throat. I want to show you a couple of things, and then it'll make sense to you on how you're going to do yours. Okay, how do I get a matrix equation? Well, bear with me here in case you don't know why I'm doing what I'm doing. You'll see in a bit. First thing I'm going to do is get what we call our coefficient matrix, in which you've seen that before. And that's to do, from Kramer's rule, we already know what a coefficient matrix is. And that's going to be the 1, a 3, a 2, and a -6. Then I'm going to get my variable matrix. And the two variables that I have are x and y. And then I'm going to have what the constants are, 9 and 3. So this is actually what a matrix equation looks like. We have the coefficient matrix, the variable matrix, and the constant matrix. Now, if you're wondering why this works, I can show you very quickly, and then move on, why this works. If you were to multiply these two matrices, you would go, this is a 2 by 2, this would be a 2 by 1, they would be totally defined, and you would end up with a 2 by 1 matrix. So I would go 1 times x plus 2 times y. I would go across and then down. And I would have only one column. So this is my only column. And then I go to my second row, it'd be 3 times x plus -6 times y. And it would be row 2, column 1. And if you look at that, that is the exact same equation you have here, x plus 2y, and then it would equal 9 from the other side. And then you have 3x minus 6y equals 3. So this is why we set up the matrix equation in this way, just in case you were wondering why that was going to work. So now that we know that it works, we want to talk more about, okay, so now I know it works, well, how do I solve it? Well, you're going to solve it with an inverse matrix, and I'm going to show you how that works. Okay? And for that purpose, we're going to abbreviate some things. We're going to go ahead and call our coefficient matrix, we're going to call it A. So the A matrix is the coefficient matrix. We're going to go ahead and call our variable matrix X and our constant matrix B. So what you really have is an equation, AX equals B. And I'm pretty confident that most of you would know how to solve this. In fact, most of you probably want to go, oh, let's just divide by A. and then that'll be my answer. Well, kind of. You can't divide matrices. You can multiply matrices, but you can't divide them. Division of matrices doesn't is undefined. It's not something that we do. So, what I do want you to be aware of, though, is if you had, I talked earlier about this kind of thing, and it's almost the exact same thing. Why is it that the division by 5 works? Think about that. Well, it's because the inverse of multiplication is division, and then it cancels, and you just get x. It doesn't cancel on this side, but it does give you the answer. So what I want you to pay attention to is that it's the fact that it's the inverse that makes it cancel. So that's why we went through all this trouble with having you understand what an inverse was. So for the future, whenever you have an equation that says ax equals b, you can take the inverse of both sides. A times A inverse times x will equal A inverse times B. So what I'm doing is I'm taking my equation here, and instead of dividing by A, I am going to multiply it by the inverse, because we said earlier that when you put a matrix and its inverse together, the identity will happen. A and A inverse together will produce I. Okay? It'll produce I. And I times x will just be x, because we said also earlier that when you have the identity times a matrix, the same matrix will result. So x will result. So therefore, anytime we have a matrix equation that is of the form ax equals b, then we can use x equals A inverse b to calculate the answer. Now it's very important that you recognize that the order in which you multiply matters. We talked about that in the previous 3.6 actually, where it does matter which order you multiply in. So if you take b times A inverse, you will not get the right answer. It needs to be A inverse times b. It needs to be in that order. Okay? So according to this, we can find our answer. So I'm going to go A is the coefficient matrix. So I need the inverse of A, and I'll times that by B and call it a day. So what is A inverse? A inverse is going to be 1 divided by the determinant. So negative 6 minus 6. Correct? If I go A times D, that's negative 6, and then minus 3 times 2 is 6. So that's going to give me negative 1/12. And then I'm going to invert negative 6 here and a 1 there. And then negative 2 and negative 3. So my inverse is going to be 6 divided by 12 is negative 1/2. Negative 3 divided by 12 is negative 1/4. And negative 2 divided by 12 is negative 1/6. And then 1/12. So this here represents my inverse for right now. And so what I need to do is calculate A inverse times B. So I want to take that matrix, negative 1/2, negative 1/4, negative 1/6, 1/12, and multiply it by B, which was 9/3. In that order, A inverse times B. And then I will get what x equals. X equals A inverse times B. So, lucky for me, a 2 by 2 and a 2 by 1 will end up giving me a 2 by 1. So I'm going to go negative 1/2 times 9 plus negative 1/6 times 3. Then I'm going to go negative 1/4 times 9 and 1/12 times 3. Okay, so 9 times negative 1/2 is negative 9/2. And 3 times negative 1/6 is going to be negative 1/2. And then here we're going to get negative 9/4. And here we're going to get 3/12, which is 1/4. So at the end of the day, we have negative 9/2 minus 1/2. So negative 9 minus 1 is actually negative 10/2. And negative 10/2 is the same thing as negative 5. And then negative 9/4 plus 1/4 is actually going to be negative 8/4. And negative 8/4 is negative 2. So it turns out that my x value is negative 5 and my y value is negative 2. And you can check that with the original problem. You can check here that x is negative 5 plus 2 times 9 is negative 2. So that would be negative 5. 2 times y is negative 4, and that's negative 9. And then 3 times negative 5 is going to give you negative 15. And negative 6 times negative 2 is going to give you, I'm thinking here, negative 6 times negative 2 is positive 12, sorry. And that's going to give you negative 3. And I'm not really sure why our numbers are backwards. That's not supposed to happen. We got the right values, but they're negative, and that's not. So now I'm beginning to wonder if 1 times negative 6, negative 6, 2 times 3 is 6, this is negative 112 times, oh, that's what I did. Okay, my bad. So basically when I multiplied here, negative times negative, that should have been a positive. Negative times negative should have been positive. Negative times negative, positive. Negative times positive, negative. So basically these were all off by their negatives. So that's going to make this be 1/2, 1/6, 1/4, and this should have been negative. So then this would have been a positive 9/2, positive 1/2, so this would have been positive 5, and this would have been positive 9/4, negative, and positive. So my bad, it's 5 times 2, which makes that 9, and then 15 minus 12, which makes it positive 3. Woo! So I hope Johnny caught that one, but if not, there you go. So that's how you do a matrix equation. So now I want you to try this one. And once you have done this, you will have completed your notes for today, and I will see you in class, and thank you for watching.